Section: Introduction. In this section, we explore sparse autoencoders, SAEs, which help us identify relevant and interpretable directions within the activation space of a language model. There is a growing interest in mechanistic interpretability, particularly in utilizing the sparse decompositions generated by SAEs for tasks like circuit analysis and model steering. SAEs achieve this by creating approximate, sparse, linear representations of language model activations using a large set of basic, feature directions. We aim for two main goals in creating a good decomposition. First, it should be sparse, meaning that only a few elements from the dictionary are needed to reconstruct any specific activation. Second, it should be faithful, indicating that the error between the original activation and its reconstructed version is small in a meaningful way. However, these two goals often conflict with each other. Typically, when we try to increase sparsity with a fixed dictionary size and training method, we end up sacrificing some reconstruction accuracy. Recent research has focused on enhancing SAE architectures and training methods to better balance these two objectives while also considering other important aspects of SAE quality, such as the interpretability and functional relevance of the dictionary directions. A common approach in these advancements is to introduce a thresholding or gating mechanism to decide which SAE features to include in the decomposition. In our paper, we present JumpReLU SAEs, which are a slight modification of the original ReLU-based SAE architecture. In this new approach, we replace the ReLU activation function in the SAE encoder with a JumpReLU activation function. This function zeroes out pre-activations that fall below a positive threshold. Additionally, we train JumpReLU SAEs using a loss function that combines a weighted sum of a reconstruction error term and a sparsity penalty, avoiding simpler alternatives like L1 loss and not requiring auxiliary tasks for threshold training. Our key insight is that, although this loss function is piecewise constant concerning the threshold, meaning it provides no gradient for training this parameter, we can analytically derive the expected losses derivative, which is generally non-zero. However, this derivative is expressed in terms of probability densities of the feature activation distribution, which we need to estimate. We demonstrate how to use straight-through estimators, STEs, to efficiently estimate the gradient of the expected loss, enabling us to train JumpReLU SAEs using standard gradient-based methods. We evaluate JumpReLU, gated, and top-K SAEs on various activations from the GEMMA 29B model, including the residual stream, MLP output, and attention output across several layers. Our findings show that, at any given level of sparsity, JumpReLU SAEs consistently yield more faithful reconstructions compared to gated SAEs. Furthermore, JumpReLU SAEs provide reconstructions that are at least as good as, and often slightly better than, those from top-K SAEs. Similar to simple ReLU SAEs, JumpReLU SAEs require only a single forward and backward pass during training, making them more efficient than both gated and top-K SAEs. We also observe that both top-K and JumpReLU tend to have more features that activate frequently, meaning they are active on more than 10% of tokens. Consistent with previous evaluations of top-K SAEs, we find that these high-frequency JumpReLU features are generally less interpretable, although interpretability improves as the sparsity of the SAE increases. Notably, only a small fraction of SAE features have very high activation frequencies, with fewer than 0.06% in a 131,000 width SAE. We also present results from both manual and automated interpretability studies, indicating that randomly selected features from JumpReLU, top-K, and gated SAEs are similarly interpretable. In the next section, we will delve into the specifics of SAE architectures, where we describe how SAEs decompose language model activations as a linear combination of a dictionary of learned feature directions and reconstruct the original activations using encoder and decoder functions. In these functions, the output from the encoder is a sparse, non-negative vector representing the feature magnitudes present in the input activation, while the decoder reconstructs the original activation from this feature representation. The columns of the decoder matrix represent the dictionary of directions into which the SAE decomposes the input activation. Section Summary. In this section, we introduce sparse autoencoders, SAEs, as a method for decomposing language model activations into interpretable feature directions, emphasizing the balance between sparsity and reconstruction fidelity. We present our novel JumpReLU SAEs, which enhance training efficiency and reconstruction quality by employing a unique activation function and a tailored loss function, demonstrating their superior performance compared to traditional SAE architectures. Section: Activation Functions. In this section, we discuss activation functions and their variations across different architectures. For instance, we utilize the ReLU activation function, while top-K sparse autoencoders, SAEs, employ a top-K activation function that sets all but the top-K pre-activations to 0. Although gated SAEs do not initially conform to the standard encoder specification, we can demonstrate that with weight sharing between the two encoder kernels, they can be equivalent to using a JumpReLU activation function. This JumpReLU function is defined using the Heaviside step function, which sets pre-activations to 0 when they are below a certain threshold. Next, we turn our attention to loss functions. Language model SAEs are trained to reconstruct samples from a large dataset of language model activations. Typically, we use a loss function that includes a term penalizing non-sparse decompositions, where the sparsity coefficient determines the balance between sparsity and reconstruction accuracy. We may also add auxiliary terms to the loss function for various purposes, such as helping to train parameters that might not receive adequate gradients or to revive inactive feature directions. It is important to note that top-K SAEs do not require a sparsity penalty since their activation function inherently enforces sparsity. Regarding sparsity penalties, both ReLU SAEs and gated SAEs utilize the L1 norm as a sparsity penalty. While this approach provides a useful gradient for training, it also penalizes feature magnitudes, which can negatively impact reconstruction accuracy. Additionally, the L1 penalty is not invariant under reparameterizations of the SAE, meaning we can shrink feature magnitudes without affecting the number of active features or the output reconstructions. To address this, we impose further constraints during training, typically by ensuring that the columns of the decoder weight matrix have unit norm. We introduce a modified L1 penalty, where feature coefficients are weighted by the norms of the corresponding dictionary directions. We refer to this as the reparameterization invariant L1, ReL1, sparsity penalty, as it remains unaffected by SAE reparameterization. We also explore kernel density estimation, KDE, a method for estimating probability densities from a finite set of observations. Given a number of samples from a random variable, we can create a kernel density estimate of the probability density function. In our work, we are particularly interested in estimating quantities related to jointly distributed random variables and well-behaved functions. Moving on to JumpReLU SAEs, these are standard SAEs that incorporate a JumpReLU activation function. Compared to ReLU SAEs, JumpReLU SAEs include an additional positive parameter that sets the threshold for each feature's pre-activations to determine if they are active. This threshold mechanism allows us to distinguish between which features are active and the magnitudes of those active features. We train JumpReLU SAEs using a loss function that includes an L0 sparsity penalty, which helps us avoid the limitations associated with the L1 penalty. The L0 penalty can be expressed in terms of the Heaviside step function applied to the encoder's pre-activations. However, training with this loss function presents challenges, as it does not provide a gradient signal for the threshold parameter. To overcome this, we employ straight-through estimators, STEs, to define pseudo-derivatives for both the JumpReLU function and the Heaviside step function used in the L0 penalty. We select a kernel function that meets the criteria of a centered, finite variance probability density function, and in our experiments, we use the rectangle function as our kernel. We also note that the hyperparameter related to the kernel bandwidth must be chosen carefully to balance noise and bias in gradient estimates. Finally, we train JumpReLU SAEs like any differentiable model by calculating the gradient of the loss function over batches of data, applying the pseudo-derivatives during the backward pass, and sending the average gradients to the optimizer for parameter updates. We provide pseudocode for the forward pass, loss function, and the implementation of the straight-through estimators in an AutoGrad framework like JAX or PyTorch. Section Summary. In this section, we discuss various activation functions used in sparse autoencoders, SAEs, including ReLU and JumpReLU, and highlight the importance of loss functions that balance sparsity and reconstruction fidelity, particularly through the use of L1 and L0 penalties. We also introduce the concept of kernel density estimation, KDE, for estimating probability densities and explain how we train JumpReLU SAEs using straight-through estimators to effectively manage the challenges posed by the L0 sparsity penalty. Section: How STEs enable training through the jump. In this section, we explore how straight-through estimators, STEs, facilitate training through the jump mechanism. We begin by understanding why this approach is effective. During stochastic gradient descent, SGD, our goal is to estimate the gradient of the expected loss, which helps us calculate updates for our parameters. Although the actual loss is piecewise constant concerning the threshold parameters, resulting in a zero gradient, the expected loss behaves differently. We can analytically differentiate the expected loss with respect to the parameters to obtain a useful expression. Here, we note that the probability density function for the distribution of feature pre-activations plays a crucial role, and we also consider the specific column of our weight matrix that corresponds to each feature. To train JumpReLU sparse autoencoders, SAEs, we need to estimate the gradient based on batches of input activations. We can achieve this using a generalized kernel density estimator, which provides us with an estimator for the gradient of the expected loss concerning our parameters. When we direct AutoGrad to utilize the pseudo-derivatives defined in our previous equations during the backward pass, we effectively calculate the batch-wise mean gradient. This gradient is then used by the optimizer to update our parameters in the training loop. Essentially, training with STEs, as we described earlier, is equivalent to estimating the true gradient of the expected loss using the kernel density estimator we defined. Next, we evaluate the performance of JumpReLU SAEs compared to gated and top K SAEs across various metrics. For this comparison, we trained multiple SAEs with a width of 131,000 and different levels of sparsity for each type, JumpReLU, gated, and top K, using activations from the JEMMA 29B model. Specifically, we focused on activations from the residual stream, attention output, and MLP output after certain layers of the model. For gated SAEs, we employed two different loss functions. The first was the original gated say loss, which includes an L1 sparsity penalty and requires periodic resampling to train effectively. The second was a modified loss function that substitutes the L1 penalty with a different sparsity penalty, allowing us to avoid the need for resampling. For top K SAEs, we used an auxiliary loss that helps minimize dead features and implemented an approximate algorithm for computing the top K activations, which proved to be faster while yielding similar results to the exact method. All SAEs in our evaluations were trained on over 8 billion tokens, and we confirmed their convergence by examining their training curves. In our methodology, we trained SAEs of varying sparsity levels while keeping the architecture and dictionary size fixed. We adjusted either the sparsity coefficient for JumpReLU or gated SAEs or the K value for top K SAEs. We then plotted curves that illustrate the reconstruction fidelity achievable at different sparsity levels for each say architecture. For our metrics, we used the mean L0 norm of feature activations as a measure of sparsity. To assess reconstruction fidelity, we focused on two metrics, with our primary one being the delta LM loss, which indicates the increase in reconstruction loss when we always predict the dataset mean. We computed all metrics on 2048 sequences of length 1024, ensuring we excluded special tokens when aggregating the results. Section Summary. In this section, we explain how JumpReLU sparse autoencoders, SAEs, effectively estimate the gradient of the expected loss during training, despite the loss being piecewise constant, by utilizing a generalized kernel density estimator. We also compare the performance of JumpReLU SAEs with gated and top K SAEs across various metrics, detailing our training methodology and evaluation metrics used to assess reconstruction fidelity and sparsity. Section: Results. In this section, we compare the trade-off between sparsity and fidelity for different types of sparse autoencoders, SAEs, specifically JumpReLU, gated, and top K SAEs, using the activations from the JEMMA 29B residual stream. Our findings indicate that JumpReLU SAEs consistently provide similar or even better fidelity at a given level of sparsity compared to top K or gated SAEs. We observe similar outcomes for all SAE types when trained on MLP or attention output activations, as illustrated in additional figures in the appendix. We also examine the frequency of feature activations. For each SAE, we look at both the percentage of features that are frequently active and those that are rarely active, which we refer to as dead features. Previous research has shown that top K SAEs generally have more high-frequency features than gated SAEs, and these features tend to be less interpretable when sparsity is low. To gather our results, we collected activation statistics from 10,000 sequences, each 1024 tokens long, and calculated how often individual features activated on randomly selected tokens, excluding special tokens. Our results, shown in a figure, reveal that for JumpReLU, gated, and top K SAEs, the number of high-frequency features varies with SAE fidelity, measured by changes in language model loss. We find that both top K and JumpReLU SAEs have more features that activate on over 10% of tokens compared to gated SAEs, although this fraction drops significantly in low fidelity and high sparsity conditions. When we broaden our criteria to features activating on over 1% of tokens, gated SAEs show a comparable number of such features to JumpReLU SAEs, particularly in the low loss and higher sparsity range. Across all layers and frequency thresholds, JumpReLU SAEs have either similar or fewer high-frequency features than top K SAEs. Notably, the proportion of high-frequency features remains low relative to the total number of features, with less than 0.06% activating more than 10% of the time, even for the sparsest SAEs. We also compare the proportion of dead features, those activating on fewer than 1 in 10 million tokens, among JumpReLU, gated, and top K SAEs. Both JumpReLU and top K SAEs consistently show a low number of dead features without needing resampling. Next, we address the interpretability of SAE features, which remains an open question in research. Previous studies have focused on the activation patterns of features, particularly the sequences where they activate most strongly. The interpretability of a feature is typically assessed by human raters or through queries to a language model. In the following sections, we evaluate the interpretability of features from JumpReLU, gated, and top K SAEs using both a blinded human rating study and automated ratings via a language model. Our experimental setup closely follows established methodologies. For each sublayer, attention output, MLP output, residual stream, each layer, 9, 20, 31, and each architecture, gated, top K, JumpReLU, we selected 3 SAEs to study, totaling 81 SAEs. We chose SAEs based on their average number of active features, specifically those closest to 20, 75, and 150. Each of our 5 human raters received summary information and examples of activations for each feature. The raters evaluated whether a feature is mostly monosemantic based on the provided information, with response options of yes, maybe, and no, along with a brief explanation when applicable. In total, we collected 405 samples, averaging 5 per SAE. In our results, we present the findings from the manual interpretability study. Assuming a binomial distribution for each rating, we report the confidence intervals for the ratings. All three types of SAEs show similar rating distributions, aligning with previous comparisons of top K and gated SAEs, and indicating that JumpReLU SAEs are similarly interpretable. Section Summary. In this section, we compare the performance of JumpReLU, gated, and top K sparse autoencoders, SAEs, in terms of sparsity and fidelity, finding that JumpReLU consistently achieves better or comparable fidelity at various sparsity levels. We also analyze feature activation frequencies, revealing that while JumpReLU and top K SAEs have more high-frequency features than gated SAEs, all types maintain a low proportion of highly active features, and we assess the interpretability of these features through both human ratings and automated evaluations, showing similar interpretability across all SAE types. Section: Automated Interpretability. In this section, we discuss automated interpretability. Unlike manual feature rating, we have proposed automated rating methods to make the evaluation process faster. The main approach we use involves two steps. First, we generate an explanation for a specific feature using a language model, and then we predict the feature's activations based on that explanation, again using a language model. This method was first suggested for neurons and later adapted for learned sparse autoencoders, SAEs. For our methodology, we utilized Gemini Flash for both generating explanations and simulating activations. In the first step, we provided Gemini Flash with a list of sequences that activate a particular feature to varying degrees, along with their activation values. We organized these activation values into bins and normalized them to be whole numbers between 0 and 10. Gemini Flash then created a natural language explanation of the feature that aligned with these activation values. In the second step, we asked Gemini Flash to predict the activation value for each token in the sequences used to generate the explanations. We then calculated the correlation between the simulated activation values and the actual activation values. We discovered that using a diverse few-shot prompt for both explanation generation and activation simulation was crucial for achieving consistent results. We computed the correlation score for 1,000 features across 3 architectures, 3 layers, and 5 or 6 levels of sparsity, totaling 154 SAEs. In our results, we present the distribution of Pearson correlations between the activations simulated by the language model and the actual activations. We observed a slight but significant improvement in the average correlation from gated to JumpReLU and from JumpReLU to another model. However, we note that the average values do not fully reflect the variation within each group. We also established a baseline by explaining the activations of a randomly initialized JumpReLU SAE for a specific layer, which resulted in random projections of the residual stream. This baseline showed significantly lower correlation scores, although it still had a non-zero average. We provide a breakdown of the results by site and layer, noting that we grouped SAEs with varying sparsity levels and performance. In terms of related work, there has been a growing interest in training SAEs based on language model activations. This interest arises from the observation that many concepts seem to be linearly represented in these activations and that dictionary learning might help reveal these representations on a larger scale. We also hope that the sparse representations learned by SAEs could better identify computational subgraphs that perform specific tasks in language models and allow for more precise control over their outputs. Recent advancements in SAE architectures, such as top K and gated SAEs, along with improvements in initialization and sparsity penalties, have helped balance the trade-off between sparsity and fidelity, addressing the issue of SAE features becoming inactive during training. Like JumpReLU SAEs, both gated and top K SAEs use a thresholding mechanism to decide which features to include in reconstructions. In fact, gated SAEs are mathematically similar to JumpReLU SAEs when weight sharing is applied, although they are trained with a different loss function. JumpReLU SAEs are also closely related to ProLU SAEs, which use a different method to train an activation threshold but do not perform as well as gated or top-K SAEs. The concept of the straight-through estimator, STE, has been around for a while and has applications in training quantized networks and bypassing defenses against adversarial examples. Our interpretation of STEs in terms of expected loss gradients is related to previous work, although it does not connect STEs with kernel density estimation. Additionally, it has been shown that models can be trained using an L0 sparsity penalty on weights by introducing randomness in the weights and calculating the gradient of the expected loss. In our discussion, we conclude that JumpReLU SAEs consistently produce reconstructions that match or surpass the fidelity of top-K SAEs and exceed that of gated SAEs at the same sparsity level. We also find that the average JumpReLU SAE feature is as interpretable as the average features from gated or top-K SAEs, based on both manual ratings and automated evaluations. Although JumpReLU SAEs tend to have more very high-frequency features compared to gated SAEs, they are similar to top-K SAEs in this regard. Considering these findings and the efficiency of training with the JumpReLU loss, since it does not require additional terms and avoids the costly top-K operations, we view JumpReLU SAEs as a modest improvement over existing SAE training methods. However, we acknowledge two significant limitations in our study. The evaluations we present focus on training for downstream tasks, such as circuit analysis or model control. Section Summary. In this section, we describe our automated interpretability approach using Gemini Flash to generate natural language explanations for features and predict their activations, which we found to improve correlation with ground truth values when employing diverse few-shot prompts. Our results indicate that JumpReLU SAEs outperform other architectures in terms of reconstruction faithfulness and interpretability, while also highlighting the efficiency of their training methodology. Section: Acknowledgements. In this section, we express our gratitude to Lewis Smith for reviewing our paper, checking the mathematical derivations, and contributing valuable insights to the SAE training codebase. We also appreciate the support and sponsorship from Rowan Shah and Anka Dragan during this project. Regarding author contributions, we note that Senthoran Rajamanoharan, SR, came up with the idea of training JumpReLU SAEs by using the gradient of the expected loss and developed a method to estimate this gradient using straight-through estimators, STEs. SR conducted the hyperparameter studies and trained the SAEs utilized in all our experiments. The training of the SAEs was carried out using a codebase designed and implemented by Vikrant Varma and Tom Lieberum, TL, with significant input from Arthur Conmee. This codebase also depended on an interpretability framework largely created by Janos Kramer. TL played a crucial role in enhancing the SAE training codebase, allowing us to effectively work on a model with 9 billion parameters for this project. TL also conducted the SAE evaluations and the manual interpretability study detailed in the evaluations section. Nicholas Sonorat, NS, and TL collaborated to design and implement the automated feature interpretation pipeline for the automated interpretability study, with NS taking the lead in scaling up this pipeline. SR took charge of writing the paper, while TL contributed to the sections on the interpretability study and additional benchmarking results. Neil Nanda provided guidance and advice throughout the project and helped edit the paper.